Module 12B, we're going to talk about surface tension, viscosity, and capillarity. It's a pretty short overall module, but I need you guys to understand and think about intermolecular forces when you think about these properties. So what is surface tension? Surface tension is the energy required to increase the surface area of a liquid. Attractive forces and minimization of energy is what causes surface tension. So it's this liquid's response to the imbalance in your attractive forces and the tendency to minimize energy. Basically, it explains why liquids form spherical shapes. Why can insects float on water? Why does the paperclip float on the water? Why do these things happen? The spherical shapes have the greatest volumes, the least amount of surface area. So if you think about the particles themselves, think about these particles in here, okay? We're talking here at the surface versus here within the liquid. Within the liquid itself, the molecules in the bulk of a liquid have more neighbors, so they experience more attractive forces than the molecules of the surface. The molecules of the surface of the liquid have fewer neighbors, so they experience fewer attractive forces. What they're going to do is they're going to form a shape to try to maximize those attractive forces. So what I mean by that is these molecules at the center, at the top here, at your surface, are going to try to form a stronger attractive force, giving you this concave shape. Concave and convex shapes. It causes concave meniscus, which we see in aqueous solutions, convex meniscus, which we see in mercury solutions. We'll talk about that when we talk about capillarity. But we're trying to maximize these shapes, which increases the surface tension of the whole surface. So increasing the attractive forces of the water in here, the water attracted to itself pulls and creates a higher surface area of the liquid, hence a higher surface tension. Generally speaking, the stronger the intermolecular forces you have, the greater the surface tension. So why? Because if I have stronger IMFs, it means they really want to be bonded to each other. They really want to hang out together. That's going to increase the surface tension and allow something to float on top. The higher the temperature, the lower your surface tension, because this is all about minimizing your energy. If I have higher temperature, then I'm giving those particles more energy just from an outside source, from an outside temperature. I'm giving them more power because I'm giving them more temperature, more heat. That heat allows me to break up more of those intermolecular forces holding these together. So these particles like here at the surface can move more. They can actually escape the solution at this point. So larger IMFs lead to a larger surface tension because stronger forces, but the higher temperature, lower surface tension because the higher temperature negates the need for those higher IMFs. Viscosity is another property that comes into play because of intermolecular forces. Viscosity is the measure of resistance to flow of a liquid. So it's kind of opposite of the way students think about it. It's basically the less likely something is to flow, the less likely a liquid is to flow, the more viscous it is. So like if we were to compare, say, water and oil, or maybe even syrup. Let's say water and syrup. Water, we all can think about just pouring a glass of water. How fast does the water flow? Pretty fast, right? Let's talk about this relatively speaking. Now, go to your fridge, pull out your bottle of syrup. Don't heat it up and try to pour the syrup. Pours pretty slowly, right? That means the syrup is more viscous. It's more resistant to flow. The stronger your IMFs, the greater your viscosity. The reason syrup has a higher viscosity is it's more resistant to flow. There's a lot more intermolecular forces going on there. Syrup is full of sugar. And so the sugar has hydrogen bonding going on, and dipole, etc., that's holding these molecules together. Water has that too, but sugar's got bigger molecules that are doing it. So it's a greater resistance to flow. Honey, same thing, greater viscosity. Lots of things in there that are causing higher intermolecular forces, causing it to flow less freely. Larger intermolecular forces result in a larger viscosity. Higher the temperature, the lower viscosity. So basically what's happening here is your intermolecular forces are preventing easy movement of the molecules. It's based on shape and size. And one if you guys have ever talked about polymers or worked with polymers, we often talk about the viscosity of polymers. Polymers you're going to learn more about them, but they're very long chains of molecules. And so these long chains can get very tangled up with each other. Not only do the IMFs, but they can get tangled themselves. And so the more entangled they are, or the higher IMFs they are, the slower they're going to flow, the higher the viscosity. The last one is capillarity. Capillarity, or capillary action, is the rising of a liquid against the pull of gravity through a narrow tube. This results from a competition between the intermolecular forces within the liquid, known as your cohesive forces, and the intermolecular forces between the liquid molecules and the tube walls, or known as your adhesive forces. So what we've got here, this is what aqueous would look like. This is what mercury looks like. And so we call this your meniscus. So this line right here, meniscus, and our concave versus convex shape. For aqueous solutions, it's actually an attractive force between the aqueous, whatever, the water and whatever's in there, attracted to the glass of the surface that causes it to rise up higher on the sides. And we see that here as well. It's this rising of a liquid against the pull of gravity through a narrow tube. Again, competition between the IMFs within the liquid itself and the intermolecular forces between the liquid molecules and the test tube walls, or your adhesive forces. The tube itself is attracted, the water molecules are attracted to that tube. So they like it. They're going to pull up on the sides and try to expose themselves to it more and get more connection to that tube wall. Mercury, on the other hand, does not like the tube you're in, and we see this convex shape instead. Mercury is trying to minimize the area it touches. It maximizes its own IMFs to not have to touch the tube. We also see this, a lot of you guys have probably done this with like art projects, etc., where you'll like put like the tip of a paper towel or maybe a coffee filter and some color, and you see the color expand across that filter. That's the same kind of concept as capillarity or capillary action, is the pull of this liquid up a porous substrate, such as the paper towel or a coffee filter. So all of these are affected by IMFs. So they're all created they're all concepts because of IMFs. Greater IMFs, the stronger we see these forces occur. As we increase the temperature of these, the forces become less important because the temperature can overcome the need for those attractive forces to minimize their own energy.